Okay, so let's go right into it. Let's jump to that first slide. So first, recall. Recall in your mind. Recall, right? The general function for exponential growth or decay is given as y equals a times b to the x minus h plus k. And that was with transformations. So what I want you to do is think for a minute. Imagine there was no h and k involved. No transformations involved here. Okay, none needed for this application. And we think of b, as a base value that can either be growth or decay. When was the problem growth versus decay? What was the difference in the b value when it was growth versus decay? What happened there?
Whether or not it was a function.
Or a? Good. Number greater than? 1. So if the number for b, if the value for b, the base, was a decimal or fraction, right, between 0 and 1, it was decay. If the value of b was 1, or sorry, I should say is greater than 1, it was exponential growth. And that's what we're seeing with this formula in red. I'm going to replace b, again, take a look at the beginning formula up here, cross off h, cross off k, and replace b with this phrase instead. 1 plus or minus r. If r is a positive value, it's going to be growth. If r, the rate, is a negative value, it's going to be decay. Think about that logically. If I tell you that the growth rate is 25% per year, well then this b value is 1 plus 0.25. So let's go through 2 examples of this so you can see that. Okay, so you can see that. And again, r is going to be defined as the growth rate. And again, a, like we did in the previous one, is like my starting value. A is my starting or initial value. Remember, it was the multiplier. It was the thing that stretched the graph or reflected it. Okay, so for a, it's going to be our starting value, and r is going to be the growth rate. Some textbooks use k instead of r. Some textbooks use k instead of r. Nothing wrong with that, just a different variable. Yeah, so for radioactive decay and stuff, it's the time units actually. It doesn't have to be years. If you're measuring things in, say the rate of growth is 25% per week, then X is measured in weeks. If the growth rate of bacteria is, it grows at a rate of 50% per hour, then X is in hours. So it depends on what the growth rate units are that indicate the units of X. Okay, X is the number of time intervals that have passed. X is the number of time intervals that are passed. So this formula is what we're going to use for the entire lesson. Okay, we're going to use this formula. Then we're going to get other formulas from this, but this is our base formula here in red that we're going to focus on.
So if R is greater than 0, is growth, and if less than 0,
yeah. When R is positive growth, when R is negative decay. When R is positive growth, when R is negative decay. And we'll see that in the next slide. So let's look at examples of this. So this first example says, if the rate of increase is 25% per day for a clothing item, rate of increase, I mean, that'd be a ridiculous increase, right? If the store just changed their price every day by 25%. But let's say hypothetically during this week, or you guys are a little bit young now, but like a lot of like clubs and bars like to do this thing where they change the price. It's the truth. When you get older, you're going to go to things like this in college, and when you're later, they like to change the price as a function of time. Why do they do that? So that people get there earlier. So their venue, their place seems to be like, there's a lot of people there. It's popular. So they make the price cheaper if you get there earlier. And as you get there later, they make the price more and more high, or a higher value. And usually people don't mind paying higher prices when they want to go in somewhere. So this is a good example of per hour, though. This would be like per clothing item per day.
Was that like happy hour?
Exactly. Yeah, exactly what happened. It's like when people go for like when your grandparents go to get dinner, they go to like the early bird special, it's called. Grandparents are like, it's a joke, but when you get older you can see this. Grandparents, like, they get up at like 5 in the morning and they go to bed at like 6 p.m. It's just a very different world, when you get older. You kind of rise and set with the sun as your body gets older. So yeah, it's like an early bird special. The same idea. The price gets higher as a function of time. So if it raised 25% per day, we could say that the R value is positive 25%, which is 0.25. Well, that gives me the formula from the last slide. It makes the formula A 1 plus 0.25 to the X, which is really A times 1.25 to the x. And we know this is growth because look, 1.25, as Alex told us, Alex said that if the b value is more than 1, then it's growth. And this is 1.25, so it must be growth. It must be growth. And then the second example, it says the decay rate. So we list the rate here as negative 0.20 for 20%, and it simply makes the equation a 1 minus 0.20. And again, we're going to have an a value and an x value when we get to the real problems, but I wanted you guys just to see how this base value changes. And here, the base, as Alex said, is between 0 and 1. It's a decimal or fraction between 0 and 1. And this indicated decay. Whereas in yellow, we have growth. In yellow, we have growth. So just simple examples of phrases that we're turning into an equation to start. But let's look at real examples with numbers and see where we're going to apply this a little bit. So let's jump into the first here. In the forest, there are currently 50 deer. Population growth and decay is widely modeled in this section. If you are into biology, if you're into science in general, this is a great application of it. Especially if you eventually become like a microbiologist or a materials engineer, where you're working on things at the atomic level, because bacteria and certain things grow and decay at rates that are like this, that are exponential. So we have 50 deer in the forest. If the population of deer increases 15% every year, how many deer are there after 25 years? So I could sit here all day and say, okay, 50 times 1.15. That'll give me the population after 1 year. Then that answer times 1.15. Where am I getting 1.15 from? Why am I saying 1.15? If you pick up on the numbers we're using right now.
It's 15%, and then will be the a value, and it's probably 1 plus r should be 0.15.
Very good. So my formula here he saw was, okay, the a value is how many deer you start with. Then you do 1 plus or minus the rate. Since it's an increase, we know it's that. And it's going to be 25 years. So this is my formula right here. Some students, when they try to derive these formulas themselves, they'll say, okay, how will this work for 1 year? And then I'll keep using my calculator over and over again on the SAT and do this 25 times. That's why you have exponential growth. That's the whole idea behind it. So this is really, if I simplify it, it becomes this. So what I was saying a minute ago was you could start, right? If you want to do this, try your calculator. Actually, let's do it. Take your calculator out. I want to prove to you how tedious it's become so that you'll never do it again. I want to prove to you how annoying this process is so you won't ever want to do it again and then maybe force you to memorize or understand what we're going to be doing here. So please take the following. Go to your home screen. We're going to make believe we don't have a formula for a minute. We're not using the formula. Go to your home screen. Type 50. Type 50 times 1.15. Enter. So what do you get? 57.5. That's how many deer are after 1 year. Now press times again. Don't press anything else. Just press times again. It should multiply the previous answer, right? It should say answer times. And do another 1.15. Seb, what do you got this time? Oh, Seb, killing me, man. I thought we had a roll going there. What do you got?
86.25.
So 50. What was the first one? Seb, go back to the first one. 66 was the first one or the second one?
Second.
First one was around what?
57.
Thank you. 57.5. Okay. So obviously, what's happening to the population of the deer? It's growing because we have an increase, right? A positive growth rate. So Seb, do you want to do this all day? Clearly, no, right? Because look at my mistakes you already made there. I mean, it's so easy. But no, it's not. I'm trying to point it out, but it's the truth. Look at that. It's so easy to make a mistake. Do this 25 times, you'll lose track. Nobody wants to do that 25 times. The number is the amount of years that pass. X. Remember, the definition of X is the time increments that have occurred. And we're measuring in years. It says, right here, this is your number, right here, that's important. 15% per year. Per year.
Actually, if you just press enter a bunch of times, it will do it for you.
Yeah, you can sit there and press enter, keep pressing enter, 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 and it'll keep multiplying. And that works, Alex. But you still have to do it 25 times, right? So what we're going to do instead is we're going to use this formula right here in red, and come up with our answer. So go ahead and plug that formula in instead. 50 times 1.15. Now the 1.15 has to be to the 25th, not the whole thing. Make sure the parentheses is not around the 50 also. The 50 is not getting raised to the 25th power.
Wait, where should we round off?
Give me the nearest deer.
So there's
What do you got?
33.
33 deer?
I did 1.15 to the 25th.
Okay, good. Times 50. Don't forget the A value right here, right?
16,000. 1,645. But it's 1,646.
If you round to the nearest deer? Okay. 1646 deer. That sounds correct. Yes, they went down as well. Now, this is an extreme example because predator-prey models in engineering, this is a big topic in engineering, study predator-prey. Predator-prey models tell you that you're not going to have just an increase, right? What hunts deer? What other animals hunt deer? Wolves, bears. People, there it is, people. The deer population is controlled by people. That's why hunting season is certain times of the year. So when the deer population spikes up, hunting season occurs so they can control it. Remind me, with 4 minutes left at 2:56, we have to pause. You have to, don't let them forget, please. Okay, there's no bell for it. At 2:56, remind me to pause. We have to do something, it says like a senior thing they do every year, because the senior's last day. So we kind of line up in the hallway and like they come down and you like, it's really whatever. I don't care. But no, you're not like going like this. No. It's just like it's a last day graduation kind of cheer because they're not in school for the rest of the year. Yeah, so it's their last day. So we just kind of cheer for them on the way out. They're over the Gana right now having a meeting. That's what you're hearing going on. Now, again, you don't want to do this all day long, right? You want to just use a formula instead. So we're going to see how this formula is going to help us throughout this process. The second example is going to be a little bit different. Let's take a look at the second example here. It says the following now. We're not looking at population. We're not looking at an actual population. We're looking at the time. It says determine when. The population of a city was 3.5 million in January 1980 and 5 million in January 1990. Assuming exponential growth, God bless you, determine when the population will reach 6.5 million. Determine when it'll reach 6.5 million. Now, the common mistake is the year, ready? January 2000. If you thought that, it's okay, but that's not right. The common mistake is January 2000, because look, ready? Watch. 3.5 to 5, how much does that go up? 1.5 million. 5 million to 6.5 million, how much does that go up? 1.5 million. So students on an SAT will see this and say, oh, it goes up 1.5 million in 10 years, doesn't it? So in another 10 years, it'll go up another 1.5 million. So after another 10 years, it'll be the year 2000, and that's the answer. It's not true though. Remember, exponential growth is not the same as linear growth. What I just described to you, deer population going up 1.5 million every 10 years, that's a slope. That's linear growth. This says assuming exponential growth. So we need to figure out what that growth factor is. We need to know what rate we're growing. So what are we solving for really first? We need to know what rate we're growing. R. So before we can even figure out X, right, determine when the population will reach 6.5 million, forget that part of the problem. Just use the first sentence here. Just use this sentence to plug in for your original formula and solve for R. It's growth, so I'm going to put a plus. I know it's plus or minus, but because this is population growth in this example, I'm going to use a plus sign here. We will, I promise, we'll talk about decay also. That'll be a minus sign. Yep, very good. So let's fill in everything we know. So right now, we know that the starting value of population was 3.5 million. Helen is correct that X is absolutely 10, because 10 years have passed between 1980 and 1990. So my starting population was 3.5 million. After 10 years, my population is now what? 5 million. That goes on the left side. Very good. So if I want to be writing these down, starting value, current value, time periods elapsed, whether they're measured in years, days, minutes, seconds, hours, milliseconds, or whatever the units are. Again, current value, initial or starting value, time periods elapsed. And then we solve for R.
Wait, sorry, the Y is the starting.
Y is the current value. Current value. And the way to check that, Alex, is look, we're growing, right? In population, so that's got to be the starting value, and then it goes up to 5 million. I can put million with all the zeros, but I'm going to just make life easier and keep everything in terms of millions. I don't want to have to write 3.3500, you know what I mean? Over and over. So I don't need to do that for these problems. How do I solve for R here? How do I solve for R? Maura, go ahead.
First we divide
Go ahead.
everything that we go
Agreed. I'm going to leave it as a fraction. That works. Next step, Maura?
by. Would you take
Yeah. Raise both sides to what power? Give me powers instead.
1 over 10?
The 1/10 power on both sides. The reason we do the 1/10 power, what happens when you raise a power to a power? Yeah, you multiply and these will cancel. A power to a power is a multiplication of those powers, and 10 times 1/10 on the right-hand side cancels. The right-hand side becomes 1 plus R. The left-hand side is whatever your calculator tells you. I don't know what that is, to be honest. I didn't write it down. I think it's, actually I kind of did. I think it's 1.036. Type it in your calculator, please.
Yeah.
Your 1/10 needs to be in parentheses when you put in the exponent. Actually, I shouldn't say that. That's not true for all these calculators, but for most things. If you have it on math type, raise your hand real quick. When you hit exponent on your calculator, how many of your calculators actually show an exponent? How many of you show a little arrow? So who shows the exponent? Does it actually show like a superscript in the top? Do you see this arrow, a little caret? So if you see a little superscript, you can go up to the superscript and press 1/10 and you're fine. But when you see the arrow, I would recommend doing it with the arrow actually, because that's the way computer coding is written. They don't see superscripts in computer codes. So with the arrow, you need parentheses for your exponent. So put 1/10 in parentheses, please. You'll get 1.036. Subtract the 1 from both sides. What does R become? Just 0.036. So that's your growth rate, around 3% per year. 3% growth per year. We are clearly a virus on the earth, if you can't tell. Humans are, we are, right? Look at that. We are the virus. When you talk about a virus is something that attacks the host. The earth is the host. We're the virus. We're depleting the earth's resources. When someone gets cancer, cancer cells reproduce over and over again, and they affect the host, right? They physically affect the host by depleting their host resources, energy. They physically change cells into cancerous cells. We, in a sense, look at population, growing 3% per year. That's huge. It's huge. Wait 20, 30 years from now, they're going to have ordinances in play that have population limits. China already does. Certain countries that have overpopulation issues have restrictions to how many kids you can have because of this problem here. Anyway, with that.
How did you get to 1.036 in your?
5 over 3.5.
Oh, wait, no, I mean the 0.036. Like,
Subtract 1 from both sides. This number minus 1. Just do it in your head, right? You're left with the decimal. Like 1.5 minus 1 is 1.
What's the point of like to the 1/10
Well, because this is to the 10th, isn't it?
Yeah.
And we want to solve for R. So the only way to get R by itself is to get rid of the exponent first, and then the 1 plus R, subtract the 1, and you get R by itself.
So you don't have to do like
Logs for this.
1.036 to the 10th like square root.
You can do the 10th root. You can do the 10th root of this whole thing, and you get the same answer. But once you do a 10 to the 1/10, 10 times 1/10 is 1. So it's not there anymore. Remember, when you have a fractional exponent or an exponent, raise it to its inverse. Have we talked about that? Like x to the 3/5. I want to get x by itself, I raise that to the 5/3. It's always the reciprocal. The reciprocal of 10 is 1/10. That's why we use 1/10 in this problem. Okay, it goes back to the beginning of that section. We talked about in like section 10.1 and 10.2.
So what is R?
R is the growth rate. It's not the answer, right? What does it say? Determine when of the population. When. So what are we looking for when it says when? What variable? when? X. X represents time increments or time intervals. So let's go ahead and take this idea and write this, please. Let's write out our general formula first. And then let's start filling in. We want to know the time when. So X is now our unknown. So I'm going to know everything else except for X. So I'm going to put a little X here already. My growth rate is 0.036. My growth rate is 0.036. So that's going to go in here now that I've determined it from the last part of this problem. My starting value is the same number, 3.5 million. We could start at 5 million, which is later in time, and do that also. It doesn't matter either way. But let's say we start at 3.5 million. And what do we want to know? When the population reaches what number? When it reaches?
6.5.
Yeah, and that goes in for Y. That's what we're trying to figure out. So ready? Take a look at this equation. We are trying to figure out X, which is when it will happen, with a growth rate of 3.6%. When we start at 3.5 million, and we're trying to get to 6.5 million. So look at the problem. There's a variable in the exponent. What do you use to solve when there's variables in the exponent? There's a variable in the exponent. You can't solve by looking at it. You have to use logs. So we're going to see logs appear here. That's why this is exponential growth and logarithms. You're seeing the applications. Divide by 3.5. Always start by getting rid of the a value when you're trying to solve for r or x. I'm just going to write this as a number now at this point, okay? Does everybody agree with me? I'm not going to put the plus sign anymore. 1 plus 0.036 is 1.036. Always start by dividing by the a value when you're trying to solve for r or x. It's going to happen many times in this section, so if you don't see that, then just write it down. If you see it, fine. Physically, you can just see what we're doing. Always divide by this first. Now, as soon as we get into this form, convert to logs. Whenever you have a number as a base and a variable as an exponent, and you're there and you're stuck, I can't go anywhere right now, convert to logs. The base remains the base. So on the next line, I'll write log base 1.036. And then I flip the other two. Remember, take this and switch their locations now with the logs. Keep the base and switch the other two. And now x is solved for. So remember, whenever you're solving an exponential equation with a variable in the exponent, convert to logs. Yes?
Do we have to now do the thing where it's like convert?
Yeah, so on your calculator, how would you answer this? How would you figure it out? What would you type in, Alex?
You do log 1.357. Let's just do the fraction form. Over log 1.036.
Very good, Alex. So remember what's called change of base. When there's not a base written, which your calculator, you can't put a base in there, it assumes the base is 10. So instead, when the base is not 10, we rewrite it with the common log base 10. I think you told us this last week, remember that's called a common base. We take the common base of both and write it as a quotient. So you take the log of the argument over the log of the base. Log of the argument over the log of the base. How many years have elapsed? What's our answer? How many years have elapsed since we started the problem, which was in 1980 this problem started? Yeah.
I got 17.5.
I got about that too. Very good. Around 17.5. 17.5. So what does that mean? Somebody tell me, what year is this going to happen? When we already happened, actually. When are we going to reach 6.5 million people? When did we reach 6.5 million people?
By the year like 2007.
We started in 1980.
Oh, we started in 1997.
Yeah. So let's point this out. This is important. I want to point that out. If we had started this problem, please take a look. If we had started this problem with 5 right here, for 5 million, there were 5 million in 1990. If we had put a 5 here, this would have come out to be 7.5.
And then
We started it though in 1980, right? 3.5 million occurred in 1980. So 17 and a half years after 1980. So in the year 1997, how far exactly? What's a half a year from January? July. Very good. Most people say June because they think June is the 6th month. It's the 7th month. It's the half year. My birthday is July 1st.
That's my mom's birthday.
Exactly halfway through the year.
That's my mom's birthday. My
Well, not
sister's
exactly. Your mom's?
Oh, that's
My
what
mom's
Dan's
my sister's half.
Really?
That's what it is.
I like July 1st because it's halfway through the year and then Christmas is
That's
the other
good, yeah,
half.
it's nice.
My cousin, December 24th. It's brutal. She gets the double gift. You know, when you get 2 gifts for one, it's like, oh, really? My brother's birthday is on Mother's Day. So his birthday just, not always, but a lot of years it turns out to be. It was this year, yesterday actually, it was his birthday. So he always gets like overlooked, you know. It's like Mother's Day takes precedent over my brother's birthday, you know. So it's bad when you share a holiday. I know that one. So anyway, July 1997 is our answer here. Okay, July 1997. Let's go on. Investments. So we're going to talk about investments next. We'll do 2 problems, and then we'll go into a little bit of half-life and doubling time. Investments are very, very similar, but they use a specific formula. Okay? Now, capital A is very much like capital A in this problem is the current amount of money that you have instead of Y. Okay, it's the same thing. This is like Y over here that we had earlier. Capital P when it comes to investments is called principal. Principal is the amount that you start with. So the amount that you're starting with in this case is the amount that you're actually physically investing. So that's the P value that you're going to put into the account. The amount that you're actually investing is this, while this is the amount that you currently have. R is still the rate, whether it's growth or decay. N is the weird thing. N is called the number of compounds per year. Compounds per year. And all that is how often your interest rate is taken into account. So if I had annual interest, it means at the end of the year, if I put in, let's say, $1,000 into a savings account, and that savings account makes 10%, at the end of the year, I'll get $100. Again, 10% is the interest rate. I put $1,000 into the account, and at the end of the year, if it's annual, I'll get $100. I get 10% of 100, or 10% of 1,000. Now, if it's compounded quarterly, you instead get a little bit of money each quarter instead of at the end of the year. And it turns out to be a little bit more money, actually. So after the whole year, instead of getting $100, you'll get like $25.10 each quarter. So it's actually a little bit more worthwhile to compound more frequently. If you compound monthly, every month you get a payment, a dividend. You get some sort of a calculation done. And it ends up being a little bit more the more frequently you actually have this. But there's a limit to the actual value. We'll talk about that in the next section, actually. Tomorrow, next section. So that's what N is. So if I say it's compounded monthly, N is 12. Let's write this down. Compounded monthly, N is 12. Compounded weekly, N is 52. Just the number of months in a year, number of weeks in a year. So compounded monthly is 12. Compounded weekly is 52. Compounded daily is 365. We'll just round. It's in a quarter, yes. Compounded daily is 365. Compounded quarterly. How many quarters are there in a year? 4. Compounded quarterly is 4. Compounded semi-annually. 2. Very good. Semi-annually, half year. Semi-annually, and is 2. That's pretty much the only word you're going to really be using for compounding, okay? We'll talk about compounding continuously, that's the other one, in the next section. Okay, so let's look at an example of this. You invest $3,000 into a savings account. I believe this number is reasonable because I made these problems last night. Savings account used to make a lot more money. Used to make we're talking like 4, 5, 7%. Now, the best savings accounts, the best, which are like CDs, only make like 3 or 4% interest. So I use 4% interest. If you invest $3,000 into a savings account that is compounded quarterly with an annual interest rate of 4%, then how much money will you have in the account after 7 years have occurred? So we go right to our formula, and it's just a plug and chug. It's just a plug and chug. We plug right in. A equals P, parentheses 1 plus R over N to the NT power. Now notice here we use T instead of X. It's just a general formula, so I wasn't going to vary it a little bit. But I used X last one, right? X was the number of time periods. T is the number of years. It's the same thing really here.
T is 7.
T is 7 in this case. Very good. T is 7. The principal is the amount I put in, and I put in $3,000. Principal, the amount you start with. P, principal. 1 plus interest rate. It's got to be as a decimal, so 0.04 over quarterly. If it's compounded quarterly, how many quarters in a year? How many? 4. And then I put a 4 here, and it's 7 years taking. So your exponent is 28, right? Your exponent here is actually 28. So we have to take the 0.04 and divide it by 4, which gives me 0.01. So this formula becomes A equals 3,000, 1.01 to the 28th power. Okay, 3,000 times 1.01. And check my math, please, but you should see it. Right? 0.04 over 4 is 0.01. There's the 0.01 right there. So you have to know your math pretty well. Okay, if you add anything to 1, you're just adding on to that decimal. What do we get for a value for this when we evaluate it? Go ahead and check for me. Go ahead, Alex. What do you got? 3963. Yes, very good. 3963. And I'll give decimals because it's money. So 87 I'll give because it's cents. So it's not bad. I mean, you make about $900 for doing nothing. For just investing money. Have you ever heard the phrase money makes money? Money makes money? It simply means that people that are born into money sometime in their life, it's very easy to make money. So whether or not you recognize that you've been born into a life where you have money and you think you don't have a privilege, you do. If you're just born without debt, you're automatically a head start about people. People that are born whose family are in debt, getting out of debt is insane because it's this with the negative. It's all decay. You're losing money when it's in debt. You're paying them an interest rate. So if you're born and your family says, oh, we're going to give you $10 million in your trust fund so when you get older you have money to use. You can just invest all $10 million at this rate, and this is a very low rate, and you make a lot of money. Because if you change this number, go ahead and change this. Alex, change it. Let's make this $10 million now. And let's put only again this amount, which is very low. 1 0, and then 6 zeros. 1 0 0 0 0 0 0 0. 10 million times 1.01 to the 28th. What do we get, Alex? Is it more than 10 million? Is it 10 million something, or is it more than is it like 11 million, 12 million? What does it come out to be?
No, you make like $3 million.
You make about $3 million? So the answer is 13 million-ish? So think about that for a second, guys.
13,210.
Yeah. So if you're starting your life with 10 million, and you can just invest it in a simple account like this, just the interest alone in 7 years, you make $3 million. Imagine guaranteeing making $3 million in 7 years. That means that you're paying yourself about $500,000 a year to do nothing, just to invest your money in a very, very safe savings account. It can't lose interest. This is not, I'm not joking about it, it's the truth. So when you have money, when you build principal, you can actually gain a lot of money by simple investments. I'm a math guy. I put a lot of my salary into my investments, a lot, like 30%, which is way more than anybody. Most people put like 5% of their salary. I put about 30% in because I know math. And over time, if I want to retire later, I know to put principal in now. Because do this now, you hit second enter, press second enter, on your calculator, Alex, press second enter, and change this number instead of 28, right? So that was 7 years. Let's make believe we're doing it quarterly. So let's make believe 15 years go by, so make that a 60 instead. Do this, same exact problem with 3,000 here, okay, but do this with a 60. If you put a 60 here, we're talking about 15 years elapsed. So 3,000, 1.01 to the 60th power. What do we get for that? See how much money we make in 60 years. I'm sorry, 15 years.
So again, put in 60 is that.
What is it?
No, put in 60 is that.
Put in 60 as your exponent, yeah. We're making this a 15 now, right here. 15 years.
You get $2,000, $2,400.
So this becomes 5,450. So even though you've not doubled your time, you made more than double what you would have before that. Like you made a total of 900, and now you made 2,400. Double 900 is 1,800, right? So you think, oh, from doubling the time, I get double money. It's not true. That's the whole idea behind exponential growth. And if you leave it in longer, it compounds interest on itself. So you want a principal that's more than 3,000. more than 3,000. So if you can invest $10,000 a year of your salary into retirement that's making guaranteed 3 or 4%, eventually that 10,000 over 20, 30, 40 years, that 10,000 you put in every year becomes almost like 50,000 a year, really, in essence. And suddenly you have millions of dollars in your retirement when you only contributed maybe $300,000 to $400,000 into your retirement because of savings. Why can banks give you savings interest? Because they take more money from other people, unfortunately. That's the unfortunate part. Banks, when they give out loans, they charge interest rates of like 8%. So you have to pay them 8%. But then they take the money, right, that you have to pay them, and they take your money and say, you invested there and you do 3%. Where's the 4% difference? In the bank's pockets. That's how banks work. Okay? So you have to understand how this society works around you. If you're making money off investments, unfortunately, somebody else is paying loans and paying debt at a rate of like 8% interest when you're only getting 3% back or 4% back. The difference there is what the bank is actually making. And this is the simplest example of this possibility. The simplest example I know right now of this possible case. Okay? Let's look at. Yes, are we exactly? We have a minute still. I'm going to finish this now. Thank you, Mr. Sullivan. So, how many dollars must be invested at 3% compounded quarterly to yield 10,000? I just want you to set it up. To yield 10,000. So I want 10,000.
So you have to find out what P is.
We have to find out what?
P.
Good. It says how much should be invested. That's what P is looking for. So we're looking for the P value in this problem. We want it to be 10,000. What does that go in for? A. You want it to be 10,000. We know that it's 3%. Compounded quarterly. I used quarterly again. Sorry, I should have gone to like monthly. For 5 years. Okay? So this is our problem right here. It's just a plug and chug. You got to get a number for this, and then divide 10,000 by that number to get P. I don't want us to miss this. So let's run down real quick. We're going to clap, we're going to come back to conclude. Open your books. Put it down for a second. We'll conclude together. So let's just go out. And let's go out quietly. Okay, let's go out quietly. We're about done, guys. We're just about done. I just want to write this down. Yeah, there's no bells, guys, so just give me a minute. So this is what we'll get as an answer if we do the math for this one. Okay, this is the principal amount invested that we need to make $10,000. So 86,1190. So we have to clearly invest a certain amount that's less than 10,000. If your answer comes out to be more, it doesn't make sense, right? Because this is growth. So if you invested, hypothetically, say your answer is 11,000, and you end up with 10,000, it means you lost money, which would mean you would have a negative growth rate. This would be a negative value here, right? So we're looking at interest rate, which is growing or accumulating money. So this P value had to be less than 10,000 as an answer. So again, I simplified this right here to become 1.0075 by adding these. This is to the 20th. You can calculate this number in your calculator and then divide 10,000 by that number. Okay, again, 10,000 divided by this quantity gives you P. There's no need for logs. Why don't we need a log for this problem to solve?
Because it's non-variable.
Very good. There's no variable in the exponent. The variable is not the exponent, it is the coefficient. The coefficient is the variable, so we can divide by its multiplier. To wrap things up, all I'm going to say is this, because we can finish this other piece tomorrow. It's fine. We could have done the last 5 minutes and probably finished this, so we not gone out there. So tomorrow, what I want to do is, say it one more time.
It was one of the ones that I did.
It was one of the ones that. Oh, so let's wait on it then until today. That's a good point, Alex. So Alex asked about number 7, but this has to do with half-life, so let's wait on this one. Any questions on other problems from 10.7 that you did last night? The word problems? Yeah, 7. Number 11? Number 11. So I give you guys section numbers. I start giving page numbers. It's so annoying to find the section. All right, page 487, number 11. How long would it take you to double your money? So this is a doubling problem, which we're going to learn today, but it's okay. Actually, it's fine because this has to do with investment, so we'll talk about it here. How long would it take you to double your money if you invest it at a rate of 8% compounded annually? So I start with this formula. To that part, you started with that, Seb? Yeah. Okay. And you want to double your money. Well, how much did you start with? Do you know?
So you can just say X. And then it can be 2X.
Yeah, so we have P already there. So let's just call the amount 2P. That's what double the money means. So again, I don't know how much money we started with, but by definition, that's what P is. P is the principal amount. The principal amount is the amount you invest. So if I invest $2,000 and I want to know when it's going to double, then A is $4,000. If I invest $5,000 and I want to know when it's going to double, then A is $10,000. But I don't have the P value. So instead, I'm going to use variables and write 2P, saying I would just want to know when this is going to be doubled, right? That's what we're looking for. And we want to know about when it's compounded annually at 8%. Compounded annually at 8%. So let's continue this. Annual compounding means N is what? N is 1. Very good. N is 1. 8% means R is? Very good. And I'm looking for how long it will take, so I don't have time in this problem. I don't know what the time takes. It says how long will it take, right? How long? So what am I solving for? I'm solving for a variable in the exponent. What do you think that involves when the variable's in the exponent? Logs. Now, before I get to logs, though, let me get rid of this coefficient. Remember I talked about that? Always divide by the coefficient first when you're trying to find something in here. Look where I'm pointing, please. Any of these things, if you're solving for any of these, you have to get rid of that coefficient first. So divide both sides by P. Well, that's nice. When I divide both sides by P, the P values cancel on both sides, making the left-hand side just equal to 2. and the right-hand side equals this. Now, instead of writing 0.08 divided by 1, anything divided by 1 is itself, right? Anything divided by 1 is itself. So this is just 1 plus 0.08. 1 plus 0.08 is 1.08. Okay, again, not to be able to see this, obviously, right? But this is itself, and when you add a decimal to the number 1, just tack on the decimal. This 1 in the exponent means nothing either, so I'm going to erase that as well. And that's what I'm left with. So this equation, when you divide by p, and then simplify inside, becomes the following, which we have here. And then, as Eduardo said, convert to log. Seb, tell me about the logs here. The base remains the base, right, Seb?
Right, so log base 2.
The base remains the base. What's the base of the exponent?
Point 1.08.
1.08. Got it.
To the second power
Of 2, Seb, of 2.
equals t.
Very good. Let's work on that, right? We have to be able to speak math as well. We talk about it a lot. So log base 1.08 of 2. That's what your answer turns out to be. Now, obviously, you have to do your calculator. You can't do this by hand. So let's use change of base. On the calculator, just go ahead and type. Oops. Go ahead and type this in. Okay, always use the common base of 10 for this. Always, when evaluating, use the common base, please. New calculators allow you to put a base down here. As much as it's tempting, please do it this way because this will play a role 100% later on in calculus. You will absolutely need to know change of base. So I'm pushing you to get used to it. Please don't use the base part here. You can do that in new calculators, but I'd rather you not. I'd rather use change of base. And that'll give me some number. Okay, and the answer will have units of years. Because this was 8% interest per year. It said 8% interest per year. For any of these investment problems, the answer is always in years. It's always in years. What's up?
Should we round in years?
Yeah, I mean, I'd give maybe a tenth of a decimal, a tenth spot.
Yeah.
Yeah. What do you end up getting?
10 to the 0.
What does it become?
I got 9.006.
9.006. So in that case, 9.0 would be the rounding then, yep. Okay, even if you gave a tenth, it would still be 9.0. If you want one more decimal, it'd be 9.01. So about 9 years later, your money will double. Your money will double. Now, does it matter? This is really where we're starting to extend the ideas, right? Does it matter what the investment actually is? If I put 10 grand in or 10 million, it's still going to double, right? In how long? 9 years. So if you want to know doubling time, you could literally always use this formula here. And whatever the interest rate is, just change. If it's 5% interest rate, 1.05. If it's 2% interest rate, 1.02. And you can solve for t every time as long as you put a 2 here. That'll give you your doubling time, which is kind of what we're going to do in today's lesson.
You probably didn't do this yesterday, but when do you know when to use the y equals a 1 plus or minus r or the 1?
So pretty much we're always going to use y equals a 1 plus, except for money problems. Money problems, we use this formula. So this formula is always for investments, okay? And this said, money was compounded. It said compounded annually at 8%. That's an indication that you're going to use a money problem. Okay? Any other growth and decay problems, you can use that other formula. Yeah? And I'll talk about doubling and half-life, which is just an application of this. And then we'll do 2 more examples. So here's what your homework is tonight. So let's take a look. Doubling and half-life. Doubling and half-life. Your book just gives formulas for these and tells you memorize them. Let me show you where they come from. Francisco, if I doubled my money today, doubled it, right? And I had $5 to start, how much do I have at the end of the day? So what percent increase is that? What percent increase? Careful. What percent increase is it actually? Not what is the new percent, what's the increase? What is it? It's a 100% increase. To double my money is a 100% increase. I do have 200% of what I started with, but it's a 100% increase. So my increase rate is 100%. So in general, for doubling, let's write this down. For doubling, we assume that R is equal to 100%. To double your money, let me put a colon here instead. To double your money, you are literally using an interest rate of 100%. Before I go on to write the formula, let's talk about halving. When you have something, what's the rate? And now obviously it's not an increase, it's a decrease. But if I have something, what percent am I taking away from it? 50%. So my rate here is negative 50%. Now, with that said, I can rewrite this formula that I started with. So go back up here, please. And just plug in for R in both of these cases. We're not going to plug in for A or X. So the formula still has A in it and it still has X in it. But this becomes 1 plus 100% to the X. 100% is just 1.00. Which really becomes this. God bless you. And that's what this becomes. This is the general formula that your book uses right here. The book gives this to you. But where does it actually come from? It comes from this formula at the top. You don't need to memorize this ever. You never need to memorize this. And for halving, what do you expect the answer to be? For halving, what do you expect the answer to be? What do you got, Isabel?
Y equals 0.5
Yeah. Y equals A times 0.5 or 1/2 to the X. Very good. So there's my two formulas. The first one is the book's formula for the general doubling, and the second is the formula for the general halving. What does A stand for? A stands for initial amount. Initial amount is A, good. Initial is important. X stands for time periods elapsed. And the Y is the current amount. The current amount, the amount right now, not the initial amount. So let's look at examples. One of the most common examples of exponential growth deals with bacteria. You learn about this in biology. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start a day with only 1 bacterium, singular form of bacteria, which can double every hour, so X is in hours now, right? Time of increments. By the end of the day, we will have over 16 million bacteria. Crazy, right? Prove this with a growth function. So let's start with our function. It's doubling every hour. And it says that we start with only 1 bacteria. So let's put a 1 in for A. Every hour it's doubling, and this happens to be what? At the end of by the end of the day. How many hours are in a day? So X is 24 time periods have elapsed. Again, it doubles every hour. This tells me that the units of X are hours. And since there are 24 hours in a day, it's important to write this as 24, not 1 day. Common mistake would be to put a 1 here for your time period and say it's 1 day. But the rate is a rate per hour. Doubling, as Francisco told us, is an increase of 100%. So this is the doubling formula, really. So instead of using this formula, I could have used this one right here, which is what this becomes anyway. And 2 to the 24 is way over, or it's over 16 million. Check it on your calculator what it turns out to be. I think it's like 16 point something. What do you got? Give me a decimal.
16.7.
Thank you. Okay, 16.7 million bacteria. I gotta keep track of the bells. 12:42. There's no bells right now, okay? So at 43 minutes. So you can, again, take a look. You can start here and go right here every time. You don't have to memorize that, but if you want to, and you like to memorize formulas, that's a doubling formula. Just plug in, you get the same thing. Plug 1 in here for what you start with. 24 hours elapsed, goes here, that becomes a 2. So whether I go this way, or just go straight down, you get the answer, it's the same thing. Again, your book gives you this formula right off the bat. So you want to use it? Go ahead and use it. They use N0 as the nominal amount invested or put in. I haven't seen N0 in a long time. Instead of using A, I'm going to keep using N. Okay, for the amount initially, instead of N0. Let's take a look at an example of life. Each year, the local youth center has a one-on-one basketball tournament. Imagine there are 64 players, similar to 64 teams in an NCAA bracket. Initially, and at the end of each round, half the players are eliminated. How many players are left after 3 rounds? Okay, how many players? And you can do the math. Half of 64 is 32. That's 1 round. Half that is 16. Half that, the answer is 8. So I know you can do it in your head by halving, right? But let's go ahead and do the process. Yeah, good.
Okay, so if you have y equals a times 1/2 to the x power,
Okay.
then y equals 64 times 1/2 to the 3rd power, and then you get 8 from that.
Very good. Okay, there are 8 teams left. 8 teams left. Or 8 players. Each player's. So that's my halving formula. And I could use 1 plus or minus r and make the r value negative 50%. And it would be 1 minus 0.5, which is 1/2. So I can just go right there. Okay, there are some tougher problems on your homework. For example, what if I said to you, after how many rounds will there be 2 players left? What are you solving for now? After how many rounds will there be 2 players left? What are you solving for?
The
Exponent. You'd be solving for x. And if you want 2 players left, this becomes a 2, and this becomes the x. More.
Why is it 1?
1/2 cubed. 1 cubed is 1. 2 cubed is 8.
Yeah, but then 64. Is it times that?
Yeah.
Oh,
These are all times, right? Times, always.
I read it as like power 1/8.
No. It's times. Remember, exponential growth is a times b to the x. Okay, so you're finishing up all the homework 10-7. Tomorrow review, Thursday test. Okay? Every day, guys. I'll try to get your quizzes back tomorrow. Because tomorrow's review day.
be a little constant.
Oh, so yeah, there's no problem set, but here's the deal. I'm not going to correct anything, but some students have asked you a question. You could just look at the homework assignments and get problems near them that are similar. So if I give you numbers 3, 5, and 7, probably do numbers 4, 6, and 8, right? So look at the evens that are in that area to work on if you want to study a little bit tonight before tomorrow, and then come in tomorrow with questions that go more on Wednesday. Helps hours tomorrow. Helps hours. No, because I never taught this lesson. And I had this from like 10 years ago, so I just put it up. But if you honestly want sample questions, come by and I'll sit with you. But all I'm going to do is look at your textbook, look at your homework, and I just pick problems on the next one you've done. That's where that comes from, to be honest. So I've never taken a test with this topic ever, so it's all brand new. You just come in there, you know, get questions tomorrow. So come in for the review tomorrow, normal during class, which will be today, day 6, right? So tomorrow I have you guys. Or not in this room. Sorry. Tomorrow I have you guys 4th period in there too. So come to 4th period, see the field, and then you freeze it for it tomorrow. Okay?
Okay, thank you.
You're welcome.
It's like 30 pounds, because the account section had it as a concept, or not too
I mean, I don't give extra credit on this class. I'll be completely honest. I don't. And even actually, Christian has to take it about extra credit assignment. I've never given ever, as a school, don't give extra credit. I mean, in my regular physics class, I give like extra credit experiments to do on their own. Because it's not an honors class. I don't do an honors class. Just so you know. Okay? But in a regular class, I'm not a good bad thing as a teacher. Okay?
And also, I was having
You did it before?
yeah, right.
In my 3rd period?
I got it 7 times.
Because it's a nice